Good morning. Even though we're in this room, this is not a colloquium talk. This is a technical talk, and the organizers of the meeting decided to put it here. As you can see, there's crowds of people standing in back. Actually, I wasn't sure that the talk would be appropriate. I am not going to be talking about infrared divergences at all, but about ultraviolet divergences. And I'm not going to be talking about de Sitter space in particular, but about what I'm going to be doing will be applicable to any kind of Robertson Walker flat space metric. But it is about loops, so that much connects with the rest of the meeting. And since a large part of the world's loop community is here, if you can imagine such a thing, I'm glad to have the chance to describe this to you. This is work that actually came out of a course I gave on the quantum theory of fields last spring, and I was trying to cover things that were not already in my 3-volume book on the quantum theory of fields, and one of them was the in formalism, and that led to this work. I'm not going to be talking about a model that is directly relevant to cosmology, although it has some similarity to the kind of thing you worry about in cosmology. What I would like to do is to describe a way of dealing with ultraviolet divergences in cosmological contexts where you calculate, for example, correlation functions that does not rely on dimensional regularization. Dimensional regularization has problems. By the way, is this clear? Is this okay? I see some people nodding their head. All right. One problem is that it's difficult to see how to use dimensional regularization unless you have an analytic formula for the various wave functions that appear in the interaction picture fields. And generally speaking, unless you have a de Sitter metric or something close to it, like slow roll inflation, you don't have analytic formulas for those wave functions. And how you extend them away from 3 space dimensions to 3 plus epsilon space dimensions, I wouldn't know. But even where the wave functions are explicitly known, there are problems with dimensional regularization. As I learned to my chagrin, Senatori and Zaldariaga last year pointed to errors in the use of dimensional regularization by a number of authors, including me, but also others, some of whom are here. I haven't checked what they've said, or whether I really haven't gone back and looked at these calculations to see whether or not I agree with Senatori and Zaldariaga. But I wouldn't be surprised if they were right, partly because they're smart people, but also because I've never really trusted dimensional regularization. There's always seemed something fishy about it, in particular the fact that when you use dimensional regularization, suddenly there are no quadratic divergences or any other divergences except logarithmic divergences, which somehow doesn't seem right to me. So in any case, whatever you think of the motivation, my aim is to try to find a way of dealing with ultraviolet divergences that preserves the underlying symmetries, which is what dimensional regularization is good for, but which doesn't use dimensional regularization. And, for example, that could be used even if all you had for the wave functions were numerical computations. where you didn't have any analytic form at all. By the way, even though we're in this room, I hope people will interrupt me if anything I say is unclear, or even if you can imagine such a thing wrong. Now, why is this not? Oh, I see, it's these keys. The model I want to choose is chosen to be simple enough so that I don't get bogged down in the complications of a fully quantum gravitational calculation, but is general enough so that it can deal with any kind of inflation, any kind of scalar field. What I take is a real scalar field in a fixed background metric. The metric is an arbitrary flat space Robertson Walker metric. That is to say, it's characterized by an expansion factor, A of t, which is completely arbitrary. The scalar fields then obey a wave equation. This is the wave equation. And as usual, I write them as a classical unperturbed term plus a fluctuation. The unperturbed term is assumed to depend only on time, and it satisfies a simpler version of the wave equation. I'm just going to go through some very familiar preliminaries before I start saying anything about divergences. We work in the interaction picture where the fluctuations are governed by the part of the Hamiltonian that's quadratic in the fluctuations, and these fluctuations obey this field equation on the top. I can hardly see the red dot. There it is. This field equation and these familiar commutation relations, and these tell us that the field is expanded in terms of creation and annihilation operators and wave functions. This is what I mean by a wave function, this u, q of t. Q is the co-moving wave number. These operators satisfy the familiar commutation relations of creation and annihilation operators. The wave functions satisfy this familiar field equation in wave number space. And there is, in addition to the wave equation, there is an initial condition with the constants and everything are chosen in just such a way that with these commutation relations, the fluctuations obey the commutation relations that they're supposed to obey. This is, I think, completely familiar, and I'm not doing anything new here. Informalism has also become familiar. If you have any kind of operator which is a product of fields all at the same time but at different points in space in general, then the true vacuum expectation value of the Heisenberg picture operator is given by a bare expectation value of a time-ordered product. Well, first an anti-time-ordered product, then the operator in the interaction picture, and then a time-ordered product, where by bare expectation value, I mean the expectation value in a state, a Bunch-Davies state, which is annihilated by the annihilation operators. And the interaction picture Hamiltonian in this model is just given by expanding in powers of delta phi, starting with the third power. Terms of second and order, of course, are in the unperturbed thing, which enters into the interaction picture. But this is the interaction picture Hamiltonian in this kind of model. I'm doing nothing more fancy than the loop expansion. That can be regarded as an expansion in a parameter g if you think of the potential as g to the minus 2 times some function of g times the scalar field. In that case, the third derivative, which enters here in the interaction, is of order g. This fourth derivative is of order g square, and so on. and in general, the expectation value of the true Heisenberg picture fields, n of them in L-loop order, will be of order g to the 2L minus 2 plus n. So L is a loop counting parameter. Excuse me, G is a loop counting parameter. A term of every additional loop gives you an additional factor of G squared. That's, again, all perfectly familiar, I think. Now, I want to talk about the ultraviolet divergences in this kind of theory. The one-particle irreducible graphs that are ultraviolet divergent are of two types. There are graphs with a single vertex stuck in a loop with any number of field lines coming out of that vertex, and graphs with two vertices stuck in a single loop with any number of field lines coming out of the two vertices. I made it 2 here and 3 here just for variety. And if I had a loop with 3 vertices, that wouldn't be ultraviolet divergent. So all the ultraviolet divergences are in one-particle irreducible graphs are of these two types. And just looking at these graphs, you can see the form of the counterterms you're going to need to eliminate the divergences. Now, you have to be careful about these counterterms. The Lagrangian is the Lagrangian. It doesn't know that you're going to put the system in a Robertson Walker metric with a given A of t. It doesn't know that you're going to expand around a definite phi bar, an expectation value. So it has to be dependent only on phi, not delta phi or phi bar, but only on the total scalar field. And it has to be written in a generally covariant way, because it doesn't know what metric you're going to use. And, but looking at these two diagrams, you can immediately see what the form, subject to those conditions, what the most general possible form of the counterterms will be. And this is it. There are three possible, well, first of all, it has to depend only on second derivatives of the potential, because that's what you get when you insert something in a line. You get the second derivative of the potential. And it could depend on the metric and its space-time derivatives, but since it has to be generally covariant, it has to take this form, the square root of the determinant of the metric, and it could depend on R. Now, of course, you can have interactions that satisfy those conditions with arbitrary numbers of powers of V second derivative and R, or even higher, even covariant scalars with higher numbers of derivatives, but you don't want anything with dimensionality greater than 4, because the only counterterms you need to cancel infinities are operators with dimensionality 4 or less. And these are the only ones. This term has, well, since V second derivative is dimensionality 2, always counting powers of energy, A will be a quadratically divergent counterterm. We're not doing dimensional regularization, so you have to take into account divergences of all orders. B and C are, well, since these operators are dimensionality 4, B and C will be logarithmically divergent counterterms. So this is the most general kind of counterterm you could possibly have. Yes? Yeah, that's a good question. You're absolutely right. You could have a term d mu phi, a V second derivative of phi. And I was just passing over that. You don't get any interaction that could produce an infinity like that. There's no general argument against it, but it just doesn't occur. And actually, you can see that from these diagrams that it doesn't occur. Why is it not going backwards? There it is. If you look at this, well, it would have to be a diagram like this, and this diagram doesn't have, there's no way you get derivatives acting on these external lines. So it's as simple as that. But you're right. In fact, I think when I write this up, I'll include that interaction. Another question? Okay. Now, it's important since the counterterms are generally covariant, or they come from a generally covariant. Of course, when I use this, I will then expand around the unperturbed scalar field. So you get an infinite power series for these counterterms, but still with just three unknown coefficients, A, B, and C. Now, it's very important that since you only have available to cancel infinities a generally covariant term here, that the calculation of the infinities has to respect general covariance, even though you are actually working with a particular metric. That means you have to use a method of regularization which is generally covariant. That's why dimensional regularization has been historically used. And if you're not going to use that, you have to use something else, at least at first I thought so, that respects general covariance. And there is a method called covariant point splitting, which has been used, applied to things like calculating the vacuum expectation value of the energy momentum tensor, but it's much too complicated to use in this context. I started out working with it, and I just gave up. I defy anyone to use that method, although there's nothing wrong with it in principle. The method that I found that is both workable and generally covariant is the Pauli Villars regularization. What you do is you add a number, in addition to the physical field phi, you add a number of heavy fields that I call chi. Can you actually see the red dot? Yeah, I guess you can. And you make the potential a function of phi plus the sum of all the regulator fields. Each regulator field has a large mass, mn square, and a renormalization constant zn. And the infinities are canceled if you choose these parameters in such a way that the sum of the zn inverse is -1, which that makes it cancel the physical field, and the sum of zn inverse times powers of the regulator mass are 0 up to the largest divergence you have. In the one-loop calculation, the worst divergence is quadratic, so you need this up to mn square, and that means you need at least 2 regulator fields. But in fact, it's just as easy to work with an arbitrary number of regulator fields. And in doing calculations, I didn't choose 2 or any particular number. I just worked with any number you like, so that the method would be workable with quartic divergences. And in the case where you have real gravitational effects, quantum gravity, you do get quartic divergences. And you would have to work with this up to d = 4, for example. And so I didn't specify any particular number of regulator fields, but just worked in a completely general way. The Pauli Villars regularization, as you might guess, was introduced by Pauli and Villars a long time ago, 1947, for applications in quantum electrodynamics. It's been applied in general relativity by Duncan and Bernard and Duncan and Vilenkin, but they applied it to the old classic problem of calculating the quantum corrections to the expectation value of the energy momentum tensor. As far as I know, it's never been applied in the more complicated problem of calculating cosmological correlations. Now, you take the regulator masses much larger than the mass is square, much larger than h square or h dot or the second derivative of the potential, and also large compared to any of the external physical wave numbers square. In the end, of course, you let them become arbitrarily large. And when you do these integrals in one-loop graphs, you have a single co-moving wave number, which I call Q. that you have to integrate over. The integral over Q is simple in two regimes, low Q and large Q. For low Q, that is Q square over A square, much less than the regulator masses square, you can simply ignore the regulators. And that is in particular true for the unperturbed scalar field. You don't have to worry about the regulators affecting the unperturbed scalar field I call phi bar. On the other hand, for Q square over A square very large compared to the Hubble constant square, H dot, second derivative of the potential, and so on, of course, that's where the regulators play an important role. But there, you can use the WKB approximation. You need an extended version of the WKB approximation, which I'll come back to. Now, the thing that makes all this possible is that these ranges overlap. Since the regulator mass is much larger than H square, H dot, and so on, you can choose you can have momenta which are both low energy and high energy in these two senses, and you can choose Q in the overlap range. In other words, you can choose Q so that Q square over A square of T is much less than all regulator masses, but much greater than H square, H dot, second derivative of the potential, and so on. And when you integrate over the wave number, you can just divide the integral into two parts. One Q less than Q, the other little q less than big Q, the other little q much bigger than big Q. And in the integral over little q much less than big Q, you ignore the regulators. And in the integral over little q much bigger than big Q, you use the WKB approximation. And you also drop terms that are convergent even before cancellations, because they would be suppressed by powers of big Q square over the regulator masses square. This is not a cutoff in the sense of usually meant. Big Q is not an infrared cutoff or an ultraviolet cutoff. It's just a place where I choose to divide the range of integration. And as long as I choose big Q in this overlap region between Q's that satisfy the first condition and Q's that satisfy this condition and Q's that satisfy, as long as it's in this overlap region, the result will not depend on the value of big Q. It's just a convenient way of dividing up the range of integration. Now, as I said, you're going to need more than the usual WKB approximation. By the usual WKB approximation, I mean this statement at the bottom of this view graph, of this slide. This is the usual WKB approximation. It's easy to correct it when you have regulator masses. You just replace Q by the square root of Q over A square plus M square, and then you have to change that A and put that into this integral. It's easy to write out what you mean by the ordinary WKB approximation when you have a mass, but you need more than that when you have a quadratic divergence, as you do in this diagram. This diagram is quadratically divergent, and here's the extended WKB approximation. I've only written it down for the thing you need for calculating that graph, which is the absolute value of Q square. For the physical particles, as long as Q over A is much larger than H square and H dot, as Q square over A square is much larger than H square and H dot, this is the this is the leading term, gives you the 1, but then you have a term which you normally don't include in the WKB approximation, which is suppressed by 1 over Q square, but does play a role in quadratically divergent integrals. And when you have a regulator mass, it's considerably more complicated, but you can work out these coefficients, and I have, and this is what you get. This includes all terms of order 1 over kappa square or 1 over m square, where m square over kappa square is treated as being of 0th order. And kappa square, as I said before, is q over a square, well, it's q over a quantity square plus the regulator mass square. Now, this is to 0th order in the potential. It's very complicated to work out the WKB approximation when you include the potential, because with the regulators, the potential term, it's a function of the scale of the physical scalar plus the regulators, and so it can produce transitions between wave functions with different oscillation frequencies, and that makes a mess in the WKB approximation. So what you do is you first work out the terms that are independent of the second derivative of the potential, and then to include the second derivative of the potential, you treat it as a first-order perturbation. Now, of course, it's not a perturbation. The second derivative of the potential, in the loop counting I did earlier, is of 0th order. So any number of insertions of the second derivative of the potential in a loop are all of the same order of magnitude. But the only one that survives in the integral for wave numbers larger than big Q is the one which is linear in the second derivative. All the others are convergent, and that means they're suppressed by powers of big Q square over the regulator mass square. And so this is all you have to include. Now, when you do that, you find that the coefficients, remember the form of the counterterms in general, there are 3 constants, A, B, and C, and A is quadratically divergent, B and C are logarithmically divergent. What you need is to choose them in order to cancel the dependence on the regulator masses. And this, it turns out, is what cancels the dependence on the regulator masses. There's a completely unique term involving the regulators. And then there's a constant, and there'll be such a constant in each one of these 3. Here it's mu a square, which can't be determined by the, well, any finite constant, of course, will still leave you canceling the regulators. This constant is not a drawback of the method. It's a physical degree of freedom. I could always correct the original potential by changing it, and I could add terms, for instance, proportional to second derivatives of the original potential. That's a physical possibility, and that's what this constant represents. It's a physical change in the theory, which can't be avoided. I mean, it's an unknown constant unless you actually measure what the potential is. And likewise here, there's an unknown constant mu b and an unknown constant mu c. Now, you might say, well, I always knew how to calculate the divergences even without a fancy Pauli Villars regulator, and now I find that the finite terms are undetermined, so why do I need all this mishigas? The answer is that these finite terms, although I don't know what they are, appear in a definite way everywhere where these counterterms enter. And that's in different terms in the final answer. So although there's an undetermined finite constant, which is physically undetermined, it's not undetermined by the mathematical method, the way that constant enters in different places is physically determined. There's no ambiguity once you've chosen the value of mu a square, mu a, mu b, and mu c. Well, anyway, this is the answer for the counterterms, and now I can present the final calculation. Well, to try all this out, I calculated the 2-point functions. That's actually where I got the counterterms from, although they'll work for any endpoint function, the same counterterms. But just to see how I calculate the finite things. In the 2-point function, there are 3 kinds of diagrams. I'm sure you've seen, in fact, even the brief time I've been here, I've already seen these diagrams on the blackboard a couple of times. There's this diagram. These are the 3 one-loop diagrams for the 2-point function. This one is logarithmically divergent. This is quadratically divergent. This is also quadratically divergent. These are the one-particle irreducible graphs. This is one particle, of course, reducible. And you use the prescription that I've described of breaking up the integral into little q less than big Q and little q greater than big Q. And here's the answer. It takes several slides, I warn you. This is just the first slide. Of course, the two-point function is an integral over an external wave number, e to the IP, y minus z. Y and z are the arguments of the scalar fields you're taking the expectation value of. And everything else following this square bracket is the momentum space Green's function. And this comes from the first diagram, this diagram. Actually, there are two contributions. One, where both of these come from the time-ordered product or both from the anti-time-ordered product. And that's what I'm showing here. That's this blue. This is the part of the integral from Q less than Q. There's the cutoff. And this is what's left over after the cancellation of the regulator terms from Q greater than Q. And of course, it depends on capital Q. It depends on capital Q in just such a way as to cancel the capital Q dependence of this integral. So this is half of the first diagram. The other half of the first diagram, where the two vertices, one comes from the time-ordered product, the other comes from the anti-time-ordered product. That term is, as Easter and company pointed out in general, that term is automatically convergent, and you don't have to, well, the part of the integral from little q greater than big Q is suppressed by powers of big Q square over the regulator masses square, so you don't have to include it, and you don't put any cutoff at all on here. This term comes from the other diagram, the other one-particle irreducible diagram, this diagram, and here's the term that comes from little q less than big Q, and this is what's left over from the counterterms after you've canceled their dependence. Well, excuse me, it's what's left over from the integral over little q bigger than big Q. I wish I used different letters of the alphabet. After you've taken the counterterms into account and canceled the part that depends on the regulator masses. And you see it involves this mu b. And finally, there's the contribution. Oh, but I do want to point out before I go on to the one-particle reducible graph, you see mu b appears here, and it also appears, whoops, I don't mean that. It appears here, and it also appears here because there's a logarithmic divergence lurking under the quadratic divergence. Now, I don't know the value of mu b. That's something that has to be measured experimentally. But what this method does is tell you that there's no additional finite constant in this logarithm. In other words, it couldn't be 2 mu b here. And I don't know if you would know that without a regulator, although I'm not sure you couldn't guess it. But anyway, in that sense, the finite terms are uniquely determined. Not that you know mu b, but that once you've defined mu b for one diagram, the way it enters into another diagram is uniquely determined. And now, finally, coming to the one-particle reducible contribution, this, again, is what you get from the part of the integral for little q less than big Q. And this is what's left over from the part of the integral with little q greater than big Q after the counterterms cancel the dependence on the regulator masses. And again, mu b appears, and mu c appear, and mu a appear. All of them occurred before. And the way they appear here is unique. As I said, the red terms represent the part of the integral left over from little q greater than big Q. Now, this at first gave me some problems, although I gather Richard Woodard solved this long ago. You see, in this one-particle reducible graph, this line carries 0, 3 momentum, or wave number. And I don't know how to define the wave function uq of t when q is 0. The definition I gave for the normalization depends on going to the limit when q over a is large compared to everything else. But if q equals 0, then q over a is never large compared to everything else. And also, I'm not sure that the arguments for the Bunch-Davies vacuum apply to q equals 0. So for a long time, I was puzzled by how to deal with this diagram. But it then occurred to me that, in fact, when you use the in formalism, you only need the commutator of the scalar fields with each other. You don't have to expand the scalar fields in terms of plane waves. And those commutators are uniquely known. And so you can actually calculate. This G represents that propagator for the 0 momentum scalar field. And G is uniquely determined just by knowing what the properties of the scalar field commutators are. So there's, in fact, no ambiguity and no infrared problem at all, even in the one-particle reducible graph. Well, I think I'm almost out of time. I probably am out of time. So I just wanted to leave some homework problems. Things I don't understand about this and that perhaps other people can answer. First of all, how is this formalism so smart? When you calculate the divergences, you're actually doing a calculation not for a general Robertson Walker metric, well, you are doing it for a general Robertson Walker metric, excuse me, but you're not doing it for a general metric. And yet the answer somehow knows that it has to come out generally covariant. In particular, if you look at the form of the counterterms, you find that, whoops, I'm going the wrong way. Yeah, you find that the infinities are just such to always appear with this combination, 6h dot plus 12h square. Well, of course, the 6 and the 12 aren't important, but the important thing is it's proportional to h dot plus 2h square. Now, you're working with a Robertson Walker metric, which you might give this as an assignment to someone who never heard of general covariance and just give him the Robertson Walker metric and say, calculate the infinities you need. He wouldn't know in advance that you're supposed to get h dot plus 2h square, but you do. I don't understand how this calculation knows that it, in the end, has to produce infinities, which could be canceled by counterterms arising in a generally covariant theory. I mean, if it didn't, you'd be in trouble. But I don't know how it... suppose I just gave you the problem of calculating the infinities that occur when you have scalar fields fluctuating in an expanding Robertson Walker metric, but you didn't know any general relativity. And then you learn general relativity afterwards, and you found that this combination h dot plus 2h square, which you found as the coefficient of the infinity, was just such as to be what appears in the scalar curvature, which is generally covariant. Actually, when you calculate these infinities, it's almost a miracle that it comes out to be h dot plus 2h square. You have lots of terms which involve different coefficients of h dot and h square, and they all add up to h dot plus 2h square. What other... I mean, is there some general rule that if I take a theory and calculate the ultraviolet divergences, then they have to be not only consistent with the symmetries of that theory, but the symmetries of any theory of which this may be a special case? This is mysterious to me. I'm not complaining. I mean, it's nice that it works out that way, but I don't understand why it does. And I'd like to find an explanation. The second question is, are the regulators really necessary? Did I have to go through all this business with regulators? After all, if I look at these final results, and I just regarded big Q as an ultraviolet cutoff, this is precisely the kind of term I would calculate that I need to cancel the big Q dependence. I wouldn't know the finite terms, but I don't know them anyway because mu b has to be determined experimentally. The only thing which I emphasized before where the regulator really plays an important role is to show that mu b enters the same way here with the same numerical coefficient. There's no 2 there or 3 here as there was in the previous graph. But you could almost guess that just from the way that this term appears. In the second place, it appears because you're calculating this graph, the graph at the bottom, and that's awfully similar to, oops, how do we get out of that? Good. That's awfully similar to this graph. And so it's not surprising. I mean, is there some argument I could give that pins down the finite terms without needing regulators? I don't know how to formulate that, but the final answer is almost obvious without needing to use regulators. And maybe you don't need them after all. Maybe just a brutal cutoff is enough. The final question is, oh, I don't want to do this. What's going on here? Well, I know the final question. It doesn't matter. The final question is, what do you do when you want to really include gravity in the problem? Of course, in the calculations I did when I first started writing about loop calculations in cosmology, I was careful to avoid dealing with internal graviton lines by treating a problem where gravity coupled to a large number of scalar fields. And you could argue that in loop diagrams, the scalars dominate over the graviton because there's only one graviton and there are lots of scalars. And I did that really just out of cowardice. I just wanted to avoid thinking about internal graviton lines. A lot of people have been braver than I have and have done calculations including internal graviton lines in the loops. I don't know how to introduce a Pauli Villars regulator for the graviton. I know how to introduce it for the photon. In fact, it was originally introduced for the photon. That's what Pauli and Villars did. I don't know how to do it for the graviton. And I'm not sure it's necessary. As I was arguing just a moment ago, maybe you don't need to worry about these regulators at all. But if you do need to, then we have to think about how to introduce Pauli Villars regulators for the graviton, heavy gravitons of some kind. And I don't know the answer to that. So this is offered really just as an introduction to a different way of dealing with ultraviolet divergences in loop calculations with the hopes that you all who are doing lots of loop calculations in which ultraviolet divergences occur will find it useful. Thank you.
Is the final result, could you backtrack just
Sure.
one or two, there, those final results.
Yeah, it starts
Is that
there.
that's the exact result, so you've manipulated the wave functions so that you made their ultraviolet divergences explicit, you subtracted them off, and that's the then exact result for that diagram, and if I somehow knew the mode functions, I could plug them in and numerically evaluate it.
Exactly.
In
fact, you would only need to know the mode functions numerically. Of course, you would have to carry the integral up to a q which is large compared to any of the other things in the theory, like the Hubble constant.
That's a very, very powerful result.
Well, thank you. I hope it's a useful result, but certainly you don't need, you're not tied to analytic forms for the wave function.
Wonderful. Do you know how to do that for an arbitrary diagram? Or were you going to write a paper or publish a paper?
Well, this is true. I'm sorry. I know how to do it for an arbitrary one-loop diagram. Right. That is with any number of external lines. In fact, there's really nothing new there, because the only terms where you need to cut off the Q at all are the terms that have either one insertion or two insertions in the loop. But, of course, you can have any number of external lines coming out of those insertions. And you have them appearing also in one-particle reducible tree graphs. Yeah, I know. That's perfectly clear. How to do this with two loops, I don't know. That is challenging because you have more than one wave number, and you have to deal not only with the case where both wave numbers are large, but where one wave number is large. I'm talking about internal wave numbers.
Right, I understand.
Where you have to deal with the case where one internal wave number is large and the other one isn't. And that's a complication I haven't even begun to think about. So two-loop graphs, I don't know.
Final question is, you've got that for an arbitrary potential. Is there any reason why I couldn't just choose the case where you could take the massless limit?
Oh, sure, but then you have to confront infrared divergences as well as ultraviolet divergences. And
but the formula
I've been leaving that to my betters.
The formula is presumably right? And
yeah.
it would just show the infrared divergence.
Right. I mean, this applies to that case also. And, of course, in some cases there, you get infrared divergences. In other cases, you don't, depending on how the expansion is going. I mean, this is a problem where the expansion is decoupled from the potential. I can make any expansion and any potential. So you could take the potential equals 0, but still have the expansion be not de Sitter, and avoid the infrared divergences that way. But I could also take the case where you do have infrared divergences. You had a hand.
Yeah, well, it was a comment really about the Pauli Villars. Isn't it true that the Pauli Villars regulator scheme respects general covariance? So that's why.
Oh, they do, of course.
So that's why the counterterms.
Yeah, it's clear that this is going to work. How can I say it? The Pauli Villars regulators respect general covariance. But even if I didn't use regulators and just calculated the divergences by putting in a brutal cutoff, I would see that the divergences involve the h square and h dot only in the combination h dot plus 2h square. Now, this is a calculation where general covariance has never been referred to.
I see, a different calculation than what you did.
Yeah, it's different, but it's the most obvious one where you just don't use regulators. You just cut off the integrals. And yet the integrals know that they have to be of a form which can be eliminated by a generally covariant regulator. How do they know that?
So I guess that the quadratic and quartic ones might go
wrong. No, the quadratic
but
ones also no problem. Quartic I haven't thought about, but
logarithms will always come out. The logs, I think, will always come out right, even with a...
Well, the logs, I'm sorry, what I said is the quadratic divergences, the question doesn't arise because those don't involve h dot and h square.
Right.
It's only the logarithmic divergences that involve h dot and h square, and they know that they come out h dot plus 2h square. And it's not clear how they know they're supposed to do that.
Okay.
Look, this is not it's not a paradox, but suppose I could imagine another symmetry. For example, general covariance might be included in a larger group, like the group of all conformal transformations, where I not only preserve the metric, but I allow the metric to be multiplied by an arbitrary function. And do the divergences preserve whatever combination? No, they don't. I mean, the infinities are not conformally invariant.
So I know in the case of the energy momentum tensor that the quadratic and quartic divergences, if you just use a brutal cutoff, will not respect the background, will not respect general covariance. But the logs do. They're just more robust.
Okay, that's a different problem.
Yeah.
There you're taking the two space-time the space points together, and that raises other problems.
Okay.
There was another, yeah.
What about potential problems with unitarity and Pauli Villars, particularly if you go into quantum gravity before you let the regulator masses go to infinity? You break the Kotkowski rules.
Well, of course, you're violating unitarity because the z's are negative. Is that what you're thinking of? Yeah. But the masses are going to infinity. I mean, all experience with quantum electrodynamics shows that there's no problem there because the masses go to infinity. So I assume there's no problem. I haven't thought about it. I mean, if there is a problem, it's because there are ghost poles, but the ghost poles are at infinite energy. So who cares?
In quantum gravity, it becomes a non-renormalizable.
Well, this is a non-renormalizable theory from the beginning. I mean, this theory I've described as a totally non-renormalizable theory if you take an arbitrary potential. I'm not limiting myself to a quartic potential. And so renormalizability is not an issue here. I don't think a student, Joel Myers at UT, is going to work at applying this to the case where you include the graviton and you include tensor fluctuations as well as scalar fluctuations. And there, as I said, you do get quartic divergences as well as quadratic divergences. But I don't think the fact that it's a non-renormalizable theory is any problem. I mean, you know, as we learned long ago in thinking about nonlinear pion Lagrangians, non-renormalizable theories are just as renormalizable theories. The infinities can be eliminated by counterterms. You just have to include all possible counterterms. So I just don't see any problem there. Yeah.
One thing I wanted to say, I don't really know how to apply it particularly to this problem, but I think it probably could be. But the whole point of the BRS approach to renormalization and regularization, as you know, is that it should be regularization independent. What you do is you make the BRS operator appropriate to this with whatever symmetry you want. You find the cohomology. You use any regulator you want whatsoever, or no regulator, just cutoffs. And the result should be completely independent, because if there's no possible anomaly at ghost charge 1, you have to have the symmetry. And that's, I think, a way of, for example, doing the general relativity part of this without using Pauli Villars, because you can't have a massive graviton, and without using anything. You can always do it that way, in principle.
Well, that's an interesting suggestion, and I urge you to do it.
Yeah. Well, that's the problem, isn't it?
I'm not disagreeing with you, but I just haven't begun to think about it, and I think it's worth pursuing. You should pursue it.
With regard to that lollipop diagram that you mentioned.
Which diagram?
The lollipop.
The lollipop diagram.
Yeah, when you do the shift in phi bar.
Yeah.
To delta phi, there is a linear term that remains, which is the three-level equation of motion times delta phi.
Yeah.
If you don't set that to 0 and you keep it, there is an extra contribution, just like an external source term.
Well, this term is, well, I'm not sure whether I'm saying the same thing you're saying, but let me try, and you can tell me if it's...
Let me finish what I...
Oh, I'm sorry, I thought you finished.
And it turns out that if you request that if you look at the full one-loop equation of motion, the correction to the equation of motion to one loop, that contribution of the three-level plus the lollipop actually cancel each other out.
No, I don't think so.
Yeah, I checked it.
No, look, I think this is true. Maybe you're right, but you're expanding around a solution of the classical field. What I do is I expand around a solution of the classical field equation. That is not the same as expanding around the true expectation value of the scalar field. Therefore, the fluctuation has an expectation value. This term represents simply the effect of that effect. And it is there. I mean, this term is there. It can be interpreted as the effect of, as an effect of the true expectation value of the fluctuation. And if that's what you're saying, I agree, but it's there. I mean, if you ask what is the two-point function, that term that I wrote down is there. You're not saying that's canceled. Are you saying there's another way of interpreting it? Okay, well then I agree with that, but it's there. Yeah, then this term isn't there. Yeah, but then you get an effect which is the same.
Yes.
Okay, all right, fine. Yes, I agree with that, and I know that. All right. Yeah, this is one way of seeing what it is. That what you're describing is another way. And in fact, I say that in the article I've written. But however you do it, the answer includes that. The answer includes this last term. I mean, you can't throw that term is there. Yeah.
Concerning the problem of gravity, right, in this Pauli Villars approach, I mean, if you just decompose the metric tensor into scalar vector tensor, then you get a transverse traceless massless graviton, of course.
Yeah.
And the question is, what's wrong with just using as Pauli Villars fields terms of the type m squared hij tt squared?
I'm sorry, say what that last thing?
If I now add these Pauli Villars fields...
Yeah, what did you say is the formula?
I add the mass term of the type m squared hij tt, transverse traceless squared. They would have the same type of degrees of freedom as graviton.
Yeah, but it would be it's not something you could get out of a generally covariant theory. And that's what bothers me.
Right, but there is no guarantee that the final regularized answer would be not covariant.
Well, that's a way of saying it. It's not guaranteed that it would be not covariant. It's also not guaranteed that it would be covariant.
And it would be worth checking, right?
What?
It would be worth checking.
It would be worth checking, yes. I agree. I'm not so sure that it's that important that it be generally covariant. As I said, the final answer I get is one you could have almost guessed. There's just a few questions like whether mu b appears with the same coefficient in all these logarithms, wherever it appears, or mu c or mu a. That's the only place where the regulator really is telling you something you couldn't immediately have guessed. And so maybe you don't need the fancy regulator scheme. And if you don't, then of course the worries about general covariance, in fact, then you don't have to use a regulator at all. But I don't know. I think we're out of questions.